So welcome back, students. In this video we will talk about refraction at a spherical surface. But before we get into it, we have to talk about something else regarding the refractive indices. So after we talk about the refractive indices, after I have given you some more information about the refractive indices, and we'll get on to do refraction through a spherical surface. So I want you to imagine two mediums. Okay? One could be water and the other could be glass. So I have two mediums. This is interface of the medium. Here I have water and here I have glass. Okay? So this is glass here, and then I have water on top of it. And let us suppose that light travels from water into the glass. So this would be the light ray, travels from water into the glass. And here I have the normal. So this is going to be the incident ray, and it will make an angle I with the normal. If glass were not there, it was full of water, it would have traveled in a straight line. It would travel like this. But now you have glass, you are getting into a different medium, and this medium, glass, is denser than water. Water is an optically rarer medium and glass is an optically denser medium. So the refracted ray will bend, instead of going straight, it will bend towards the normal. Instead of going like this, it will bend towards the normal. So I got this R. So this is the refracted ray and this is the angle it makes. Then I can come up with this ratio of sine I by sine R. So what does this give you? It gives you the refractive index of glass with respect to water, the refractive index of the second medium with respect to the first medium. Okay? So you get this. This is going to be mu glass with respect to water. So 2 with respect to 1. Okay. And I also told you that refractive index is simply the ratio of the speeds. But when you do the ratio of the speeds, like sine I is here, right, in this first medium, you are going to have the speed of light in the first medium. It's going to be the speed in water, right? Water divided by speed in glass. So the speed in the first medium divided by the speed in the second medium. That gives you the refractive index of the second medium with respect to the first medium. So this is what I've got. So I've got this. Refractive index of glass with respect to water is equal to the speed of light in water divided by the speed of light in glass. Okay. Well, I've told you that when you generally talk about refractive index of a medium, when you say the refractive index of water is 1.33, it is always with respect to vacuum or air. The perfect definition is with respect to vacuum. With respect to vacuum, the refractive index of water is 1.33. With respect to vacuum, the refractive index of glass, maybe a particular type of glass, is 1.5 or 1.51, 5.2, 4, 1.48, something like that. Depending on the glass, you will have different refractive indexes. But let's say it's 1.5. So if the refractive index of the glass is 1.5, what you mean by that is, this is the refractive index of glass with respect to vacuum or air. Vacuum, let's keep it vacuum. Okay. So this is what it is. So what I'm going to do now is that I'm going to do a little bit of manipulation of this equation. Okay. I'm going to multiply this with C and divide that with C again. Okay. Now I'll take this set. Okay. And I'll also take this set. Let's see what this is going to give me. So I'm going to write C by Vg multiplied by Vw by C. But what is this? C by Vg. C by Vg is a refractive index of glass with respect to vacuum. Just think about it. This was refractive index of glass with respect to water. Likewise, this term alone is the refractive index of glass with respect to vacuum. Okay, so that I will call as simply Ng. That is refractive index of glass. Okay, and now what is this? Vw by C. I'm going to make some more, I'm going to do some more manipulation here. So I'll keep C by Vg straight away, and this I will write as 1 by C by Vw. Okay? Can I write it like this? If I write C by Vw, then Vw will come up. So that's what I'm going to write. So this C by Vw is what? That is the refractive index of water with respect to vacuum. So I'll call that as 1 by refractive index of water. Obviously, with respect to vacuum is understood. So this is Ng and this is Nw. So this will give me Ng by Nw. So you see, the refractive index of glass with respect to water is actually equal to the refractive index of glass divided by the refractive index of water. Okay. I want you to understand this difference. This is the same as this one. But when we define the refractive index of glass with respect to water in terms of the speeds of light, it is refractive index of water divided by the refractive index of, the speed of water divided by the speed of glass. But if you define it like this, the refractive index of glass with respect to water is the refractive index of glass divided by the refractive index of water. So both are equivalent. Okay. So now the refractive index of glass with respect to water is simply the refractive index of glass divided by water. So this looks more natural if you think about it. In the first case, you are reversing the order. The refractive index of glass with respect to water was the speed of water divided by the speed of light in water divided by the speed of light in glass. That is how it was. But now it is simply the refractive index of glass with respect to water is refractive index of glass divided by the refractive index of water. So this makes things a little more natural. Okay? I can either use that or this. I am free to do either. Okay. So that equation becomes sin I by sin R is equal to refractive index of glass with respect to water. I'm using capital G, right? So water is equal to the refractive index of glass divided by the refractive index of water. See, makes sense. Same thing. Hope you understand this. Now, let us look at refraction at a spherical surface. So all along we took a plane surface, and then we said there was this incident ray, normal, and the refracted ray, and you found IR, and then you found the refractive index and stuff like that. But this time we are going to look at a spherical surface. Now we have two mediums. So there is medium 1 here and medium 2 there. Okay, so this is medium 1 and this is medium 2. Now there is an interface between them. But this time the interface is not a plane surface but a spherical surface. Like that. Okay? Let's imagine that from this point forward you have, this is medium 2. This could be water again, this could be glass, doesn't matter. So this is the second medium. So you have a different medium here. So this is a different medium throughout. Okay? So it's a different medium. This is one medium, this is another medium. Okay? Now, let's suppose this is the axis of the sphere. That's how it is, the axis of the sphere. So, light ray will travel, let's suppose the light ray travels from medium 1 into medium 2. Obviously, you need a source, you need an object from where the light ray will travel. You can choose any object. It can be a line object, a point object, or it can be a two-dimensional object, three-dimensional object. It can be anything, but light from the object will come and hit this surface and then gets refracted onto the other side, and it will form an image there. Because this is a continuous medium. This is also a continuous medium here. Let's look at it. But what I'm going to do now, I'm going to take a point object. Okay? I can do it for any object, but to make things simple, I'll just take a point object. And I can keep the object anywhere, but let me just keep this object here. So this is my point object. Okay, this is my object. Okay. So now this is going to send out light in all different directions. And the light, if you think about it, there is this cone of light. Let me use a different color now. Light will go in all different directions. Okay, and here, everywhere. Here, it will go everywhere. But you see, on this surface, the light is hitting this ocean. And so I'm not bothered about all the other light. I am bothered only about the light that falls on this spherical surface. So I told you, because of its spherical nature, all the rays that fall on this will converge on the other side at a particular point. But I don't need all these lines. If I take just two lines, any two lines, and if I make them obey the law of refraction, then the point of their intersection will be the focal point. Will be the point where all the rays which fall on this surface will meet. That's where they'll form the image. So all these millions of rays that are hitting the surface will converge at a particular point. And to find that point, I don't need all these million rays just 2 rays are enough for me. We have discussed this many times before. So we'll do the same. So let me just take this ray. Okay, there is a ray, this way, right? But now you see, it's hitting the surface and it should obey the law of refraction. But where is the normal? Well, the normal for the surface at this point is also like this, right? The normal is also like this. So what will happen? This ray will get into the other medium undeflected. There is no change in path. It will just keep going straight because it is hitting the normal, right? The point at which the normal, it is in the same line as the normal. So it will go undeflected. Sin I by sin R. I is 0, so sin 0 by sin 0 again. Okay, so 0 by 0 is what you will get. So you need to get, right? And this will go straight. This line will go. I've taken just one line here. Okay. So this is O. Okay. Now, let me take another ray, any ray, within this one, right? So this is second ray. I'm taking that second ray. Let's say this hits this surface at point M. Okay. Now, what would it do? It will undergo refraction and it will obey the law of refraction. So what does the law say? It says that you need to find incident angle, right? So for that I require a normal, right? So this normal at this point will go somewhere like this. So this is going to be the normal. So notice that the normal is actually the radius of the sphere, correct? So it will go through the center. So this will be the center. The center of the spherical surface, that is C. Okay, and so if there is a slit here, it will make an angle I with the normal, and now it will get refracted. If this medium was not there, it was the same medium, there is no second medium, then the ray would have gone like this. But now you have a different medium and there is a normal. Suppose this is optically denser than this medium, then this ray will bend towards the normal. So it will bend towards the normal and then it will go like that. So you notice here, this ray goes like that and this ray goes straight like this. You see, and they meet here. So this is the point where this object will form the image, right? And all the other rays which are hitting on the spherical surface will go through this point. Okay? But I'm not going to worry about any other ray because I found the point. I'm using these 2 rays only to find the point, and I found the point. Stop with that now. Okay. Now, this is my I, and this is going to be my R. This. Okay. So, that's a normal ray, you understand this. So, what I'm going to do is I will just draw this vertical line. Okay. And this is N. And if you are going to talk about, paraxial rays, which are very close to the axis, or when the radius of curvature is really big, then I can say that this is almost close to this. Okay, so this is, we call this as P or something, and it's almost close to S1. Okay, very close. So I can kind of ignore this. I'll come to that later. So I've drawn this. Okay, so this is vertical. So this is I, this is R, and I got a few triangles there. And from those triangles, I'm going to find I and R. So I need to find I and R. First of all, what is this I? This I is actually, if you take this normal, 180 degrees minus this angle, okay, will give me I, right? So 180 minus this angle will give me this. But what is 180 minus this angle? For example, okay, let me take this angle, I'll call this as theta 1, and then I'll call this as theta 2, and then I'll also call this as theta 3. Let's look at it now. Theta 1 plus theta 2 plus this angle, I'll probably call this as theta 4. Okay, so I know that theta 1 plus theta 2 plus theta 4 is equal to 180 degrees. Okay, but what is theta 4? So theta 4, or I'll do it this way. Okay, what is I? I is equal to, if you take this straight line, the whole angle is 180. 180 minus theta 4 is equal to I. So 180 minus theta 4 will give me I. From this equation, I can get that. So I can get this, right? 180 minus theta 4 is equal to theta 1 plus theta 2. So my I is equal to theta 1 plus theta 2. So this is my equation. Okay. Can I do the same thing for R? Okay. So R is actually, this is theta 3, or I'll call this as theta 5, this angle. Okay. So what have we got here? R plus theta 5 plus theta 3 is equal this triangle, 180 degrees. So what is my R? R is equal to 180 minus theta 5 minus theta 3. Okay? Okay. Look at these two angles, theta 2 and theta 5. You know, this theta 2 plus theta 5, theta 2 plus theta 5 gives me, theta 2 plus theta 5 gives me 180 degrees. So theta 2 is equal to 180 minus theta 5. Right? Theta 2 is 180. Theta 2 is 180 minus theta 5. That will give me theta 2. So I can put it here in this equation. So then my R is given by this expression. This is equal to theta 2 minus theta 3. So this is my equation 2. I found I found R. My I is theta 1 plus theta 2. My R is theta 2 minus theta 3. So I am able to express I and R in terms of this angle, and this angle. Okay? Right. Let's see. Now, let's find out theta 1. So what is theta 1? Well, I'll say, I'll do tan theta 1. Tan theta 1 will be mn by ON, right? Tan theta 1 mn divided by on. Tan theta 2 is equal to mn divided by nc. Mn divided by nc. And tan theta 3 is again mn divided by ni. Okay. I said they are all paraxial. So which means these rays will make very small angles. Okay, they are very close to the axis, so they will make very small angles. So theta 1, theta 2 and theta 3 will be very small angles. So they are very small angles, and I can say tan theta 1 is actually equal to theta 1 in radians, and tan theta 2 is theta 2 in radians. Tan theta 3 equal to theta 3 radians. So you notice here I found theta 1, theta 2 and theta 3 like this. Okay. Okay. Now, so we'll keep it like this. So what do you think is the refractive index of 2 with respect to 1? So refractive index of mu 2 1 is equal to sin I by sin R. So refractive index of 2 with respect to 1 is this, sin I by sin R. Okay. But what have we just found? We have found that this is equal to refractive index of 2 divided by refractive index of 1. We just saw that. So sin I by sin R is equal to n2 by n1. Now this is refractive index of 2 with respect to 1, but this is refractive index of 2 with respect to vacuum, and this is n1 is refractive index of 1 with respect to vacuum, right? So this is the general numbers that you use, 1.33, 1.5, so those are the numbers you have. So now if I take this here, if we use this, then I'll get n1 sin I is equal to n2 sin R. Okay. But what do we know? Again, for paraxial lines, I and R will also be small, so sin I can be taken as I, and sin R can also be taken as R. Okay. So I'm going to put this here. So instead of sin I, I'm going to say n1 I equals n2 R. Get this. How can I substitute this? That's going to be equal to n1 into theta 1 plus theta 2 is equal to n2 into theta 2 minus theta 3. Okay? So, what is theta 1? So, theta 1 is mn by OL. So, n1 into mn by OL plus mn theta 2 is nc is equal to n2 theta 2 mn by nc minus theta 3 mn by ni. I can divide both sides by mn, where it's common. Okay, if I divide all that, then what I'm going to get now? I'm going to get N1 into 1 by ON plus, okay, I'll do it. Okay, and then 1 by NC equals N2 into 1 by NC minus 1 by Ni. So this is what I get now. What else can I do? I can take N1 inside, so N1 by ON plus N1 by NC is equal to N2 by NC minus N2 by Ni. Let me rearrange stuff. I'll bring all the NC's to one side, take Ni to the other side. So that will give me N1 by ON plus N2 by Ni equals N2 by NC minus N1 by NC. Okay, and that also gives me, this is equal to N2 minus N1 by NC. Okay, I'll do it here itself. Okay, so if you bring it here, then that becomes N2 minus N1 by NC. Okay, so this is the equation to get. Now look at this. ON is almost equal to the object distance, right? This is actually ON, this is your U, okay, and this is your V, and look at this, the center to this one, this would be equal to your R, right? Okay. But your N is slightly different, but if you consider paraxial lines, we have already seen that, you know, the drop, the difference will be very, very, very small. So this distance can be ignored. If the curvature is more, then this distance could be ignored. So I can take ON as U, roughly. I can take Ni as V, roughly. I mean, if you're dealing with paraxial lines, then this will perfectly work. I mean, the approximation is very, very, very accurate actually. And NC can be taken as R. You see, it's like that, because I can ignore this small distance. If you consider paraxial lines or the curvature is small in a sense. Okay. If the radius is too big and the curvature is too small, then I can ignore this, which I'm trying to say. So I can use U and V in place of ON, Ni and R in place of NC. The only catch is that I have derived this by taking the absolute values. I've just talked about ON. I didn't talk about negative ON, positive ON, nothing. I just took ON and said I took Mn divided by ON. Likewise Mn divided by Ni. I took only the distance, length, without the sign. But the moment I'm going to use U, V and R, these things, then I'm going to use the sign convention. I told you U, V and R cannot be used without the sign conventions. The moment you say U, it will always have a sign associated to it. Okay, let's look at this. So, which is a positive direction, which is a negative direction? Light is traveling in this direction. So that is, whatever I measure from this point in this direction is positive. And if I measure something in this direction, that is negative. Because light is traveling in this direction. That's how I've drawn this picture. So, this Ni or this V is positive. Then R is positive again in this case. But look at this U. U is negative. So what I should do? Wherever I have U, because this is all done with positive numbers, this equation I have arrived at with all positive numbers. And if I want this equation to work with sign convention, then wherever I get a negative number, because U is negative, U will be negative. Negative number, then I have to convert that into a positive number, right? Okay. So what will happen is that I'll take what is N1, I'll take N1 now, N1 is divided by ON. Okay, this is like ON is what? It is actually U. U is a negative number, but what I've got here, this has to be positive, so I will say this is minus U. U is negative because I measured U as a negative number, and minus of minus will give me this positive thing. Perfect. Then come here. N2, I can't do anything good. Then Ni, that is approximately equal to V. V I'm going to measure as a positive quantity. This is also a positive quantity, Ni, so I don't have to do anything to it. So I'll just take it as a V. Okay, and here, from here. N2 can do nothing, N1 nothing. NC, right? How will I measure it? I'm going to measure it from here to there. So that is also a positive quantity. And here also the whole thing is positive, so I just take it as well. I'm done. Okay? So now if I rearrange this, I'll get this. So it's going to be N2 by V minus N1 by U is equal to N2 minus N1 by R. Now V, U and R are with sign convention. So this is the expression I get. So N2 is the refractive index of medium 2 with respect to vacuum. And N1 is the refractive index of medium 1 with respect to vacuum. And U, V and R are going to be measured with the sign convention. So V will be positive, I am okay with it. U will be a negative quantity, so negative of negative, this term, whole thing will become positive, like this. I am good. So this is what I get. So this is the equation. Okay, it's very important that you understand this. So we will do example 9.6 now. Light from a point source in air falls on a spherical glass surface with refractive index n is equal to 1.5 and radius of curvature 20 centimeters. The distance of the light source from the glass surface is 100 centimeters. At what position the image is formed? That's the question. So, example 9.6. So I have air as a medium here, this medium 1, and medium 2 on the other side, so I have a spherical surface. Okay, so this is continuous medium, all glass. Here all air. Okay. Now, you can do this. If you take a point source, then clearly this ray will go undeflected because it's going through the normal of the surface, and this ray will get deflected and then it will meet this ray here. So this is where the image will be found. So this is the object and that's the image. Okay. And they say that this is 100 centimeters from there. And they have also given you something else. It's a refractive index of glass. So this is glass, right? So this is glass. So refractive index of glass, or 2, let's say this is 2, is equal to 1.5. That's given. And this is air. So what is the refractive index of air? It is 1. It is as good as vacuum, right? Almost. So N1 is actually 1. So N1 is 1 and N2 is 1.5. So what do we know? We've just derived the formula. The formula says that N2 by V, the formula says N2 by V minus N1 by U, N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is a formula. What is R? The R value is given already. R value is actually 20 centimeters. That's the radius of curvature. So you got everything here. You just need to find V, right? Okay. Now, what is your U? Okay, first of all, when I say R 20 centimeters, is it positive or negative? Because you have to use a sign convention, right? So this is the position. Light travels in this direction. So R is here, right? This is R. This is R. So R is the same. R is going to be measured in the same direction as the direction of light. So that is 20 centimeters. So this is positive. So no issues. And what about U? U is 100 centimeters alright, but then it is going to be measured in the direction opposite to the direction of light. This is going to be your reference point. Okay. So your U is equal to minus 100 centimeters. Okay. So that's it. This is important. Your R is plus 20 and then your U is minus 100 centimeters. And you plug them in and you get this. What is N2? N2 is 1.5. V, you don't know, you are going to figure out. And minus, what is N1? N1 is 1. What's your U? U is minus 100. These are in centimeters. Okay, you can convert them into meters also, but let me do that in centimeters. This is equal to, what is N2? N2 is again 1.5. What's your N1? N1 is 1. So divided by what is R? R is plus 20. Okay, so that gives you 1.5 by V plus 1 by 100, minus or minus plus, and that is equal to 1.5 minus 1 is 0.5, so divided by 20. So that gives you, what is 0.5 by 20? It's going to give you 1 by 40. So, you can do this. 1.5 by V is equal to 1 by 40 minus 1 by 100. So, 400 could be the LCM. If 400 could be the LCM, what am I going to get here? So, I need to divide it by, I need to multiply that by 10 times, 10 by 10. So it's going to be 10. And multiply this by 4. 10 minus 4. Okay, so this is going to be 6 divided by 400. So 1.5 by V is equal to 6 divided by 400. So if I reverse this, what am I going to get? V by 1.5 is equal to, invert this, 400 by 6. So V is equal to 400 by 6 into 1.5. So 6 and 1.5 will have 4 here. So V is equal to 100 centimeters. You got positive. You don't get a negative number, which meaning the image is in this direction. So on the other side of the surface, it's in the glass. And the image is formed in the glass medium. Okay, so this is how you do this problem.